Okay, hello everyone. So this is day 4. We're going to talk about data visualization, which is going to include stem plots, frequency tables, frequency, and histograms. Alright, so to get an overview here, we have already discussed introduction to statistics and lots of terminology, which was involved in statistics in general and also in studies. And here we are now, data visualization. Following this, we're going to talk about percentiles, which is measures of standing, and quartiles and box plots, and then we're going to talk about measures of center and spread. So lots of different ways to describe data. The goals for this lesson are to become familiar with the many forms there are out there of data visualization. So I've got a number of exhibits for you to see. We also want to know how to construct a stem and leaf plot, which we will discuss, and then we want to understand what frequency data is and means, and be able to construct a frequency table and a histogram given a data set. So that's what we're going to cover today. The very first type of data visualization I want to look at is the pie chart. We're all pretty familiar with this, the percentage of a particular category. This is for categorical data. The percentage of a particular category is visually demonstrated by shading in a part of the circle that is equal to that proportion. So this is 55% of the circle. Okay, anyway. And then this one right here is a very natural pie chart. The pros are these are good for displaying a few proportions. You can't display too many. It gives a visual representation of apparent size, which is pretty good, but it can be deceptive if you have a pie chart that's on its side, right? These 3D pie charts. It can be very deceptive. Once you add that third dimension there, one category appears to be significantly larger than, say, something in the back, if that makes any sense. Generally, a pie chart is just not my favorite way of doing it. And when you do a 3D pie chart, even though it looks cooler, it's actually can be more deceptive. So, okay, cons. Quantity is represented by slices. Humans aren't particularly good at estimating quantity from angles, which is the skill that is needed here. And then also small percentages, which might be very important, are very tricky to show. Okay, another example of a pie chart. All right, the next chart I want to talk about are bar charts. So these are a lot better at showing relative size. It's very easy to compare the relative size of different categories. They can be tricky though. Watch the axes, and what I mean by that is take a look at this example right here. So this is something from some newspaper clipping. It looks like that the Times has more sales than the Daily Telegraph, and it looks like the Times is more than double the sales. Do you see that? Looks like this right here is more than double the sales. That is not true at all. They're actually very close. The way that they achieve this deception is by starting the bar chart at 420 rather than way down here at 0, where they would look a lot closer. Anyway, so watch the axes, though. People may try and trick you. One question I want you to have in mind as we're looking at all these data visuals is this display, is it easier to read this display than it is to read a table? Another chart that is related to a bar chart is called a Pareto chart. So on a bar chart, if I may just pop back up here, these are organized, I guess, by category, and you don't really take into account the size of the bar chart is. A Pareto chart is organized according to quantity or proportion. You have the largest proportion is at the top, and then it goes down from there. This allows you to compare similar values much more easily. If these numbers weren't here and this was in alphabetical order by category, it would be very difficult to tell which one was bigger. Australia's military spending in 2023 or Italy's or Poland's. It'd be very difficult to tell which one was more, which the whole reason you're sort of mapping these out all together so that you can tell which one is more. So the Pareto graph makes that easier. This is a neat trick. It's a good thing to do. Just go ahead and put the numbers right there so you can see the numbers as well as whatever you can gain visually from the size of the bars. Okay, let's see, more on the Pareto chart. So like a bar chart but arranged in decreasing order, is this easier to read than a table? Yeah, it is. If you are looking at questions like which is the least upwardly mobile country, if the table was in order from least to greatest, then it would be very easy to see that South Korea is the answer there. Which is the least static? Okay, now, how many tables would it take to organize that in an efficient way, to organize this data here, in an efficient way? It would take maybe at least 3 tables where you could put this value, order it as well. But because we're fairly good at comparing sizes visually, we can get this sort of information pretty easily. So which is the least static? Let's see, which one is this one? Let's see, this one here, just by looking, is a pretty good candidate for the least static. And now let me just check again. Yeah, it doesn't look like, oh, no. 45 is smaller, actually. Oh, but up here at the top, South Korea, that's the smallest. So, which one is least static? That would be South Korea. Which one is least upwardly mobile? Well, that would be the Czech Republic, way down there, thanks to our Pareto chart. We don't have to go far to see that. Which is least downwardly mobile? And that would be South Korea. Well, I think it's South Korea anyway. Yeah, just glancing at it, yeah. The 3 is the smallest one there. Which countries have the smallest gender gap in post-secondary education? So I look at this next plot right here, which talks about percent of people who attained education beyond high school as of 2014. We see here that there's a gender gap in almost in all of these. A higher percentage of women are getting educated beyond high school than men. And where is it least? Well, just by glancing at this, we can see that the answer there must be, it's Germany here, where there's the smallest gap. So this would be Germany. Okay, this is called a Gantt chart. A Gantt chart is a bar chart, but the start of the bar is staggered according to some other bit of information. So we really have like 3 bits of information here in this chart. We have a start time, an end time is all very easily referenced, and then visually represented by the size of this bar is the duration. So this is the time between inventions or patents and the first federal regulation. So railroads were developed very early on, and it went 60 years, about 60 years before there was a major federal regulation. Okay, shows the relative size of categories, but includes other information as well. Which invention had the shortest unregulated time? Shortest unregulated time, right there, nuclear energy. That little green square is the smallest, and that might be easier to read. That information might be more readily accessible than the number. And then our unrelated times, I would say not significantly so. And that term there, significant, is a very important term in statistics. Yes, it could be argued that they are getting shorter, but, is it really? And so significance in statistics helps us to kind of answer that. Is it really, or is it a fluke? Okay, does this mean the government is becoming more regulatory in general? And the answer to that is, well, no. And the reason that I would say no is because this is just such a small handful of technologies being investigated here. And we really can't say anything in general given such a small sample. Okay, the next sort of plot I think we're pretty familiar with is the scatter plot, but this one has a sort of a new take on it. It shows a little picture of the food. And so this significantly, in my opinion, enhances the readability of this scatter plot. Okay, let's dig into the scatter plot. So a scatter plot allows you to look at two different variables. So in this case, we have a big list of foods. Associated with each food is the percentage of all Americans that say that that food is healthy, and that number is plotted on the x-axis. And then on the y-axis, you have the percentage of nutritionists that say that this food is healthy. Two different variables for each one food. And then you plot it. So the granola bar, for instance, and it's a little bit vague, but we don't need to be precise here. The granola bar, it looks like about 70% of Americans say that that food is healthy, whereas only 25% of nutritionists, of professionals, say that that food is healthy. And it's similarly with frozen yogurt. Lots of Americans like to say that it's healthy, which is probably contributed to by advertising, but only around 30% of nutritionists say that that food is healthy. Oh, interesting. Same with coconut oil. I know my mom loves cooking with coconut oil. She thinks it's really very healthy. And maybe it is, but nutritionists, it looks like less than 40% of nutritionists would say that. Okay, interesting. All right, now, so this helps us to identify certain trends. Usually, the public and the nutritionist view agree to a point, but there are certain foods that there's a big disparity. Okay, those are the sorts of trends that become apparent here, big picture stuff. What does it mean for a food to be above the line? Okay, interesting. Well, for a food such as popcorn, let's say, to be above the line, above this line, well, that would mean that more nutritionists say it's healthy than the average American. Okay, this is a little quiz. 2 questions here. This quiz is to demonstrate that these scatter plots can condense a lot of information into one area. And so I want you to look at this plot, read everything, and try and answer these questions. And also take advantage of these examples here that they put in. These examples are nice because they kind of helped me at first to kind of understand what was going on this plot. Some plots that have a lot of information it takes time to read them. So take a little bit of time and try and answer those questions. Remember, I or the TA will be looking at slides that you've submitted, and we'll be looking for your answers here, and you'll be graded according to completion. So please take a look at that. Okay, data visuals. Now we've got bubble charts, and bubble charts are nice. So the size of the bubble indicates a variable. All right, how are the bubbles arranged in the spending plot? Here's the spending plot. Geographically, they're arranged geographically, which facilitates me looking up a particular country if I know where it is geographically. So here we have North America, there's United States. This one here must be Canada. This one here must be what? I guess Mexico? Would you say Mexico? But then again, what are all of these? Well, I mean, this one here is probably Brazil. Yeah, this one here is probably Mexico, I guess. And then you've got a bunch of, these might be like the Bahamas. Anyway, so it's arranged geographically. Okay, now this in and of itself would be a sort of a bad plot, but I just took a picture of this plot from a website. Now, on the website, you could hover your mouse over every one of these little dots, and it would tell you the name of the country. So space does not permit the name of the country to be on every little dot. And so they use technology here. If you hover your cursor over it, you get the country's name and spending. And so that's very useful. Okay. Next question. Okay, scratch out this, please. Sorry about this typo. What is the size of the bubbles in the fertility plot? Right there. That's what it tells you. The bigger the bubble, the bigger the population. So a bubble about that size right there, that's 1 billion. That represents 1 billion people. This is a scatter plot and a bubble plot. How are they arranged? They are arranged by fertility. So the fertility rate, which is described right here, is the y-axis. The size of the bubble is the population. Again, this plot, which there's a link to this plot that you can look at. You hover your mouse over each little dot and it tells you the country that it is. Okay, great. All right, let's go on. This is another bubble chart. The bubbles don't need to be round. This one talks about abortion legislation. Okay, time series plots. So a time series plot plots a variable over time, and this also allows you to see trends and identify certain events or patterns. So a lot of you are probably more sports savvier than I am. You might be able to look at this peak right here in, I don't know, what would that be, 2015, say? You might be able to look at that peak and tell me what it was that caused that peak. Maybe a particular team, an underdog team or whatever, what did really well that year, and what corresponds to that trough. Monthly prices for a dozen eggs. We have this pattern here. There's this interesting decline here at around, 2016. Right off the initially, it makes me think about what happened in 2016. We got a new president. Could that have changed it? I'm not sure. The makeup of Congress was changed, and those sorts of legislative things could have played a role here. Or it could have been something else in 2016. Around here, we have inflation going on. This plot right here, average game duration, this is of Major League Baseball. Here from 2022 to 2023, there was a significant decrease in the average duration of games. And that's because, and I didn't know this before seeing this plot, but I read the article associated with this. There was a number of rules changes that occurred in between those seasons. Some of these data visuals can be very, very different from each other. So this is a plot here. This is a chart that gives us, this right here is a chart that gives us migration. The width of the arrow gives you a sort of a relative size of how much is migrating in that direction. So very little people in North America move, whereas many, many, many people in Asia are moving. This right here is a word cloud. They have questions and they allow participants to respond. And this could be something like, what is inflation hitting hardest on? Something like that. And they'll say, 904 people said gas. 455 people said milk, and so on. And so the size of the word, the font size indicates the number of times that word showed up in responses. Here is another plot geographically arranged. These are states in the United States, and there's a lot of information here. So these are the major coronavirus vaccination barriers. And so there was a study that quantified the historic unvaccination rate, socioeconomic barriers to some extent, and then low health resources. So all of those, each of those is given its own dimension in this chart. And so that's why it's radial. A 5-factor radar chart. Here's all the 5 factors. So what you can do is you take the area of this portion here, and if it's a lot, if it's big, if the area is big, then that means there are lots of barriers. If the area is small, then that means that state scored pretty low on each of those barriers. And so what they do is they they give it a color, they give us a color bar, and the area tells us whether what the overall level of concern is. Okay, now let's look at stem and leaf plots. So this is a way of organizing univariate data. So you just have one list of numbers, and you want to look at trends and pick out patterns from this. And so we're going to organize it into a stem and leaf plot. And I'm going to do this by example. The example here is going to be the heights of the players of the Phoenix Suns, which is a basketball team in Arizona. And so the way that you do this is you go ahead and you draw a table. On this side is going to be the stem. On this side is going to be the leaf. So the first thing we need to do is we need to find the lowest number here. The lowest number, it looks like, is 74. So 74 is the lowest number. What's the highest number? 87? Is it 87? Yeah, the highest number here is 87. And so then what we do is we take each of these numbers. The last digit is the leaf. And so I put the 4 there, and the first digit or digits is going to be the stem. So there's the 7. Now, and now we go through and we're going to take each of these numbers. So 74 is on our chart. And so now what we're going to do is we're going to go down and go from the bottom to the top and just represent each number here on our stem and leaf plot. Okay, so I'm going to take the 75 as the next one, and the stem is there, the 7, and I'm going to put the 5 right there. So there is the 4 and the 5, they both have the same stem, and the leaf is the last digit. All right, so let's go. I see a 76 here. I don't see any more 75, so I'm going to go on to 76. So the 7 is already out front here. I'm going to put down the 6. I'm going to cross it off so I don't double count it. Here's another 76. Another 76. Another 76. 4 76s. Oh, actually, there's a fifth one there. 5 76s. 1, 2, 3, 4, 5. Okay. Okay, what's next? 78. There's no 77s. Okay, so 78. There. 78. Another 78. Right there. Okay, I think that's it for all the 70s. So now we'll do 80. So 8 is going to be the next stem. And I'm going to go ahead and plot that. Put these values now. So first is 80. So there's the 0. And that takes care of that number. And then there's an 81. So I'll put a 1 there. Then there's an 82. Right here. And another 82. Okay, that's it for the 82s. 83 is the next one. And then another 83. And then lastly, an 85. Okay. So certain things we can see here. There are more people who have a height from 70 to 80 inches than there are from 80 to 90 inches. There are 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 players that are in the 70s in their inches of height, and 1, 2, 3, 4, 5, 6, 7. 7 players who are in the 80s for their height. Yeah, so there's our stem and leaf plot. Okay, a frequency table now. So what a frequency table does is it assigns, this is also used to summarize univariate data. Okay, and so what it does is it lists all the values and their frequencies. So the first value is 74. How many times does it appear? Just once. I'm looking at my stem and leaf plot. You know what? Let me grab this stem and leaf plot. There it is. So there's my stem and leaf plot. Okay, so 74, what's its frequency? 1. The next number is 75. Now, what is its frequency? Also 1. Then we have 76. What's its frequency? 5. It appears 5 times. Go on to 77, which does not appear at all. So there's my frequency chart. I have every number here represented only once, and it tells me how many times it appeared in the list. Relative frequency. For this one, I'm going to copy my frequency chart. Okay, here it is. I'm going to add a column to this, and that's going to be relative frequency. And what I'm going to do is I'm going to divide by the total number of data. So the data in this case is 17. And that is my relative frequency. These numbers right here form my relative frequency. And this is my relative frequency chart. So what this tells us is that 5.9% of the people on this team are 85 inches tall, and 29.4% of people on this team are 76 inches tall. So that relative frequency allows us to get a proportion. Now what I would like to talk about is bin frequency tables. So when you have a lot of data, you don't want to list out every single value. Instead, you put certain values in classes or bins. Let's take a look at this data. The smallest is 73. The maximum is 85. So that includes 85, take away 72, and that gives me 13. Now, I took away 72 because I want to take away the inches that are not included in my data. 73 is included, so 72 and below is not included. So I'm just going to subtract 72, and that's going to give me 13. So there's 13, a maximum of 13 different numbers in this data. And so I'm going to want to divide this into bins of 3 inches, which will basically mean 5 bins. 4 bins will have 3 possible heights in it, and then 1 bin will have just 1 possible height in it. That's the 85. Okay, so let's go from there. So I'm going to have my bin here. The frequency will be here. Okay, so let's write out my bins. The first one will be 73 to 75. So that'll include 73, 74, and 75. The next one will be 76 to 78, including 76, 77, 79, 78, sorry, and so on. So, now that I have the bin or the classes labeled, now I need to find the frequency for each class or bin. I start with this 73 to 75. Okay, that's that one there. There's going to be 4 of those. The next one is going to be 76 to 78. So those will be included. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15. Now for the next bin, 79 all the way to 81. If I count that out, I get 15. And then the second to the last bin goes from 82 to 84. So that'll take us right there. So that's going to be 3. And then the final bin just has these 2 85s in it. So that is my binned frequency chart. With a binned frequency chart, we can now make a histogram. A histogram is a plot similar to a bar chart, except bar charts you usually space out the bars for the categories, but a histogram you put them together. They abut. So let's go ahead and draw this. So you start by drawing your axes, okay, and then we are going to, let me go ahead and take my data. Okay, so I have here at the bottom 73, 75. Let me just label it every 2. Okay, so the first bin, this green one, is going to go from 73 to 75. And it will include 75. It will include 75 and go all the way to 76. And it's going to go 4. So about like that. The next one is going to go from 76 through 78. So it's going to start here and go all the way. It'll actually end right at the start of 79. And it'll go all the way up to 15. So that's the second bin, the second class. And then the third class is going to start at 79 and go all the way through 81 to 82. And it also goes up 15, and so there's that. The fourth class starts at 82 and goes to, starts at 82, goes to 84, which ends up all the way at 85. And that one was only 3. And then for the final one, goes from 85 all the way to 87. And that's my histogram. The class width is 3. One way you can determine class width is to subtract the first of 2 consecutive classes. 73, this one here, the second class starts at 76. I take the difference of those, 76 minus 73, and that gives me 3. So that's the width of that class. The lower class limit is are these values right here. These first values, those are the lower class limits. The upper class limits are these right here. For the midpoint, what you're going to do is you're going to take the lower class limit, add half the class width. So that means that the class midpoint for the first class, which is from 73 to 75, that whole class is going to be 73 plus 1.5, which is going to give me 74.5, which is halfway between where that class began and exactly where the other class began. And so that's my midpoint. So take the lower class limit and add half of the class width. So histograms come in 2 forms. You could have a raw frequency histogram where the y-axis is frequency, or you could have a relative frequency histogram where the y-axis is the relative frequency. That's the case in these 2 histograms. So in both of these histograms, the ages of the first-time mothers were written down, and there's a lot of them. I don't exactly know how many are in this study, but less than 2% of those first-time mothers were 15 years old. So there's 15. About 4% of those first-time mothers were 16 years old. This was back in 1980. A very small percentage were more than 40 years old. Anyway, but we can see that there's a peak here at 19 years old. That doesn't mean that the majority of women were 19 years old when the majority of first mothers were 19 years old. It just means that the highest percentage of mothers from a single age, that age was 19. Okay, and so this is the spread, and then it tapered off there. Now notice that in 2016, this histogram has a very different profile here. We still have a peak. Well, the peak at 19 has been shifted to the peak at 20, but we also have, and it's been moderated quite a bit, and we have another peak here at 28. Okay, so that's a histogram. Exactly. Histograms display continuous data. There is usually no space between the columns. Okay, what we did today was we looked at a lot of different types of data visualization. We observed that it was much better than a table or a long list of numbers. We observed that it was much better than a table or a long list of numbers. We constructed examples of a stem and leaf plot, a frequency table, relative frequency table, and then finally the histogram. And I'll just say, in closing, that histograms are very, very, very important. And we will be looking at histograms throughout, especially when we talk about probability distributions. They're very, very important. Okay, everybody, have a wonderful day, and we'll see you in class.